And let me make the last couple of, okay, we are now recording, so let me make the last couple of announcements. First, and sort of foremost, the student course evaluations have been opened. Done it? Fantastic. Okay, excellent. Rest of you, please do it sometime between now and the end of the term. Preferably sooner than later, because toward the end of the term you tend to forget things, so try to get it done. But if you do want to wait and see how that final goes or whatever, you can do that, but please don't forget to do it. Okay? And then the one other, those who are graduated, did y'all do your CAP exam? Okay.
Yeah, we did it Monday.
What's that?
We did it Monday.
Oh, you did? Okay. So those were happening this week. I don't remember how long into the week, but anyway. Yeah, that's what I heard. In fact, one student said it took her close to 2.5 hours. I don't know. Were they timed or?
Yeah, it was 3 40-minute sessions.
3 40-minute tests. Okay. Yeah, that would have been about an hour and a half, right?
It's 2 hours. I think it was 2.5 hours almost.
Yeah, well, that's what she said, but then 3 40-minute, unless there was lots of time in between or something. I don't know.
There's only like 3 tests. It's writing skill.
Yeah. Wait. 3 times 40 would be 120. That'd be 2 hours. Yeah. And then if you had a little time in between, right. So 2.5 wouldn't be out of the question. Okay. So those are the major announcements I know about. Let's get set up for today. And before we get started, let's talk a little bit about what today's schedule will be. We're going to have about 2 hours of class. We're starting with electric current today, which is on page 147 or thereabouts. And we'll get far enough to have a lab. So the first 2 hours will be in class. And Camp's here.
Oh, we got some others rolling up.
What's that?
We got others rolling up.
Okay. Well, all 3 of my Jacobs are here, so that's good. Okay. We'll have 2 hours of class, 2 hours of lab, and 30 minutes of test. The test will be Chapter 4 test, last 30 minutes today. The lab, I don't think will take all that long. It will take a little while to set up, but not too bad, I don't think. Okay? So, any questions on anything we've covered up till now? Okay, I know y'all should be and probably are fairly familiar with most of what we're talking about. So, last time got up through electrostatics, static electricity, and now we're starting on the process of moving charges, not static charges, but moving charges. And this would then be, anytime there's a charge moving, basically you have a current. So earlier we dealt with electrostatics. The charges were more or less fixed in place. Now they're allowed to move, and that creates an electric current. Now, it's often called a flow of charge. Electric current, a flow of charge. What's the reason for it? You have a potential difference. If you don't have a potential difference, it's not going anywhere. Nothing moves without a gradient of some nature. You lift the book, it falls because there's a gravitational potential gradient. Heat goes from hot to cold because there's a temperature gradient. Wind moves from high pressure to low pressure because there's a pressure gradient. Jeremy's here. In your garden, the weeds grow into the garden because there's a concentration gradient. Well, that's a little dumb, but that is true, okay? So everything moves with a gradient. That's what you have here. You have a potential, electrical potential gradient, and that's what creates the motion of charges. Good to see more people coming in. Mason's here, and Terrence is here. Okay. Any others? No. All right. So you have a flow of charge. In reality, is there that much charge flowing? Not really. We'll talk about that a little bit later. Really, the movement of charge. There is charge moving, but it's not really flowing like you would think. Because if I could get Camp to turn either off or on the light, they come on like that. Does that mean those charges flew through those bulbs that fast? Not really, okay? What you have happening, and we'll talk about this later, but it really isn't so much the flow of charge. And we have Trevor here. Yeah, okay. All right, but we're going to call it that for now. It's better than the flow of energy. Energy, there isn't even any substance there. At least with charge, there are charges there, okay? The reason for the charge flow is the potential difference that you have. So what is an electric circuit? Those are structures designed to localize, I don't like the word utilize, but use currents, okay? Now there's several features about circuits we'll talk about, and that's going to be the major lab, part of the lab today is going to be electric circuits.
We're going to get the shock somebody?
Hopefully not,
Why not
okay?
utilize?
What's that?
Why not utilize?
It's just, why not use? It's a simpler word, says the same thing. Yeah, why use 3 syllables when you can use 1? I'm just lazy, okay? Okay, it sounds fancier, but why? It's use, okay?
Everybody needs to have that kind of thinking.
What's that?
I said everybody needs to have that kind of thinking.
Yeah.
Use simpler words.
Yeah, in my mind, I'm a simple person. So. All right, so let's look at electric circuit. What's the structure of a circuit? Well, you got to have something to make the charge moves, and what's that? Say again? Yes, a potential difference. You can't have anything moving unless you have a gradient, a potential difference, and that's your voltage source. Now that's also the energy input. Can anyone remember what a volt is? What actually that unit stands for, a volt? A volt is a joule per coulomb. What is a joule?
Work.
Yes, that's work or energy, exactly. And a coulomb? It was on the last one, it's not on this one, charge. A coulomb is the unit for charge. So it's how much energy each unit of charge has. That's what a voltage is. So that's your energy input. However many, how much charge you have times the voltage, that's how much energy you have. It's necessary for continuing flow. You do not have the movement of charge unless you have a potential difference making it move. All right, so we have that, a voltage source. Then you have your circuit elements, okay? A lot of you, and I like to call it the load, okay? It's the elements, the energy are used up either as heat, light, work, sound, you know, whatever you're using that for, those are your circuit elements, the load that's on the system. Now, they left out something here. It's really pretty important. The pathway. If you don't have a pathway, you don't have a circuit, okay? You got to have a closed loop, completed path for your electric circuit to work, okay? Now, this will be part of the lab today too. We have, electricity is rather odd in some ways, and some people blame it on Benjamin Franklin. I don't know if it was his fault or not. But in just about everything in physics, your movement follows the gradient, right? I've said that several times now. You go from high potential to low potential, okay? Now, electricity, because you have 2 types of charges, positive and negative, positives go one way, negatives go the other. So both of them can't be going from high potential to low potential, can they? Because they're going in different directions. Your potential is one way or the other. So your current flow convention is always, the conventional current is from high potential to low potential, just like everything else through the external circuit. Okay? But, and we're going to get to this a little bit later, but what usually is the charge carrier that's really moving? The minus charge. So that's going to go from low potential to high potential because it's negative trying to go to positive. So that will be the little problem. We'll get to that later. We're going to use what they call a water pump analogy. And why they put a slash there, I'm not sure. Okay? But here is your typical circuit. Okay? Voltage source, potential difference, energy source, whatever you want to call that. Okay? That maintains the potential difference. Now, there's nothing on here that indicates which way is which. But if this is the positive pole, your conventional current flows from high potential to low potential. Okay? That is the conventional circuit. We'll talk about later what happens otherwise. Here is your load. This happens to be a light bulb. The work is done there, producing the light. Now, what produces the light? Okay, heat does. You're absolutely right. If this is an incandescent light bulb, sure enough, you're heating that filament up hot enough it glows. Okay? Now, if that was a compact fluorescent or a LED, other things are causing. But anyway, that's what's producing the light. The light is the energy that's being used here. The voltage source supplies the charge with energy. Joules per coulomb. Every coulomb gets so much energy. Okay? The coulombs, the charges, move through the wires. Okay? And then here at the voltage drop, are you using up your charge? Is that what's happening? No, why not? Say again? Yes, the charge keeps moving. You're using the energy from the charge. So what you have here is a voltage drop. You have a voltage rise here, and then a voltage drop here, and you come back and start the whole process over again. You're absolutely right. You don't use up charge. You use up the energy of that charge. Okay? And then you have the conducting wires. Without the conducting wire, you have no circuit. Without a voltage source, you have no movement of charge. And without a load, you're just burning up your wire. Okay? So you basically have to have all three of those elements. Make sense? Okay. We haven't gotten to the water pump analogy. Here it is. All right. Here we have a water pump pumping water up into the upper reservoir. Okay? And so water is up here, running out of the upper reservoir, turning a water wheel here, and then the water goes back in, the pump picks it up, and starts the process over again. Now, how is this an analogy to our electric circuit here? What is analogous to what? Yes, it is, because that's giving energy to the water. Here it's gravitational potential energy because you're pumping the water up. So it's just like the voltage source is giving energy to the charge. So what would the water be equivalent to? The charge. Okay, very good. Now, what about the paddle wheel? That's the what? Was using the energy, the load. And our other one, that was the light bulb. Okay? That's what's using the energy to turn the paddle wheel. And then it starts again. Now, all analogies generally are going to fall apart somewhere. Where does this analogy sort of become unlike the previous one? What would be the pipes here? What would that be equivalent to? No, the current would be the water. The what? No, the source is your pump. What would be the pipes here? The wires, exactly. The transmitters of that. Now, what happens here if the line springs a leak? Water flows everywhere, right? Sprays, whatever. What happens here if the wire springs a leak? Yeah, no leaking. current doesn't go flying everywhere like water does. So that's where it sort of falls apart. You break the wire here, everything stops. Nothing completes. You break the line here, you get a mess. Okay. So all analogies will fall apart somewhere. But that's a pretty good one, the water pump analogy to the electric circuit. Okay. So what's the nature of current? Okay, now this is where we hit what I was starting to talk about earlier, but here we go again. Historically, the nature of the electrical fluid, just like they thought we had heat as a fluid, caloric, which we didn't, but here the electrical fluid, historically, they had no clue what it was. What do we know it is now, mostly? Or we at least think it is now. Electrons, okay? That's usually what's carrying the charge, is electrons. Okay. In your battery, is it just electrons carrying charge? No, you got ions, okay? Positive ions moving this way, negative ions moving that way. Okay, so you have ions moving, and the negative ions are usually associated with electrons. So actually in the battery you have charges moving in both directions, but in the line, generally you only have electrons moving, okay? But that's really, we'll get to that part later, a little bit later. So here's where the conventional current had you moving from the positive to the negative, because you're going from high potential to low potential. What's wrong with that picture? There would have been positive charges moving that way, but we know in reality very few positive charges move very far at all, period. It's usually the negative charges are providing most of the current flow. Okay? So your conventional current always going from plus to minus, but your actual electron current, which is really what's carrying most of the charge, is from negative to positive, because electrons are negatively charged. And that's what they sort of blame on Benjamin Franklin, or at least I've heard him accused of that. When early in the thing, they knew there were two types of charges. They just were trying to figure out what do we call them. He said, well, let's call one positive and one negative. Let's do the electrons negative. Just sort of arbitrarily there, then he has it set up so everything's moving in the wrong direction. Kinda, not quite. You'd still have a problem here because even if they were named opposite. So, anyway, you have conventional current plus the minus, but electron current is minus the plus. Okay? The current is thought to be a flow of positive charge. In reality, you know it's not. Protons don't move much at all. In reality, it's much more complicated depending on the material. Like I said, here in the battery, you have positive charges moving one way, negative charges moving the other. That's a lot more complicated. But the opposite is correct in the metals and the current. It's usually electron flow. But even that is not a really good picture of it. It's still more complicated than that. But when you have charges moving, it's usually electrons. They're light, they're mobile. Protons are not. Ions are generally not. That can happen in a battery, but it doesn't happen in a wire too much at all. Okay. So what are these current mechanisms? What is it that makes them happen? Okay. Now, I really regret this, that they're leaving off a lot of formulas. And I'm going to have to go, oh no, they're just out of place. Okay. Were you saying something? Okay. All right. I figured he would be. Okay. Here are your current mechanisms. In liquids and gases, and by the way, in the battery, what's in most of your batteries, especially automobile batteries? Second? Yeah, you got sulfate ions in there, okay? Exactly. Sulfuric acid is the liquid in there. So you're talking about liquids and also gases, as in the fluorescent tubes. Now, they're not really, it's gases in there, happen to be ions. Okay? Both positive and negative charges move in opposite directions, always, with gases and liquids. okay? But with your metals, which most of your wires are, and other things, what we have are what they call delocalized electrons. Quite often we just call them free electrons, okay, like Free Willy or something like that. They're able to move throughout the metal without being attached, say, this is my atom, that's my atom, I can't leave it, They're free to move as sort of a cloud. They call them electron gas. I prefer the concept of cloud, but same type deal. The electrons move. Now, here's why I said it's still a confusing picture, because the drift velocity of electrons is extraordinarily slow. If Camp were to turn on the light or off the light, that's not electrons racing from the switch to get to the tube. Like that. Not happening. In fact, what's happening with those electrons?
It's sending a signal to turn on something bigger.
They're what?
It's sending a signal to turn on something bigger.
Okay. Actually, those electrons, what kind of circuit is that?
AC.
AC. They move a little bit one way, a little bit the other way, a little bit one way. They really don't go anywhere much at all, except back and forth and back and forth. Very fast, back and forth, but they don't go very far at all. So no, it's not electron racing over here. It is, and I think this may be what Camp was referring to, it's the field that's set up instantly. Not the movement of charge, but the field. We'll get there in a bit. The actual drift velocity of electrons is extraordinarily, exceedingly slow. It's the electric field. Here it is right here. The electric field moves through the conductor at nearly light speed. It's not a material, so therefore it can happen very, very rapidly. Not quite up to the speed of light, but it sets up and activates immediately. The electrons that are right near the switch, as soon as they move, every electron in the whole circuit, including these right here, move at the same time, because the field is set up basically almost instantaneously. Not quite. Close to light speed, but not quite there. Okay, so here would be the situation with no field, except it's not nearly that regular, okay? You don't have a bunch of negatives and a bunch of positives, things like that. No, that's not how it looks. They're sort of scattered all over the place. But as soon as you impose a field, now what is, and Charles decided to show up today. Alfred said he wasn't coming. No, I'm just kidding. He said you were coming. Okay. I'm trying to get him in trouble. Okay. It's nothing pretty picture like this. They're all scrambled in there. But as soon as you induce a field, then we talked about this before, didn't we? What is the convention of the direction of a field? Yeah?
From high potential to low potential.
Second?
From high potential to low potential.
Okay, exactly. It's the direction that a small positive charge would move if there was a small positive charge there. So if the electric field is in that direction, a small positive charge would move there, meaning your electrons would tend to move this way. So what they show here is one electron. As soon as that field is introduced here, it then is attracted to a nearby positive, and then to another one, to another one, to another one. Now, this is still very regular, because actually when they do come close to each other, they can bounce off each other. This actually may recoil a little bit and then pick up again. It's a torturous route. Not just always in one direction. The trend is in one direction, but it's a mess. It's a real mess as it goes, and it's a very slow mess as it goes. But the electrons very slowly drift down the wire, okay? Nothing like instantaneous. The field is instantaneous. The electron movement is really, really slow. Slow drift component added by the electric field, okay? But the field goes at nearly light speed. So that's what's really creating the action, is the field, not the movement of charge. The charges do move, of course, but that's not the big operator. Okay. So here's how we define current. Current is charge per unit time. Now, if you think back at the beginning of this course, first thing we talked about was a displacement or a distance. And then once we got that concept down, we said, well, what's the time rate of change, of course, of distance or displacement? And that gave us velocity or speed. And well, once we had a velocity, what's the time rate of change of velocity? How does velocity change with time? That's an acceleration. Later we talked about momentum. The time rate of change of momentum, force. Okay? When we talked about work, the time rate of change of work, power. Everything we hit just about, we talk about the time rate of change. So when we have charge, positive charges, negative charges, whatever charges, if they're moving, there you got a current, and the rate at which they move, the time rate of change of the charge as it moves, that's your current. So what's the unit? The unit is ampere. Now why would they have a capital A here? Named after Louis Ampere, okay, a French physicist who did a lot of the early work with that. And what is that unit? An ampere is a coulomb per second. Charge is coulomb, time is second. Coulomb per second. I is current. Why they use a capital I, I'm not sure. Why it's even an I, I'm not sure. Charge is little q. Remember, capital Q in the last chapter was heat. Little q in this chapter is charge. Charge per unit time, coulombs per second is an ampere. Capital A. And by the way, Coulomb is capital C because it's named after, I think it was Charles Coulomb, okay? Whatever his name was, okay? Second's not named after anyone, therefore it's a little s. Okay, and remember, degree C, capital C, would be degrees Celsius. If it doesn't have a degree, C means Coulomb. Okay. Now, we've already mentioned two different types of current. What are they? DC and AC. DC meaning? What do we mean by direct current? Flows generally just in one direction. Charges move only in one direction. The field is in one direction, pointing in one direction. Now, what uses DC circuitry? Cars do, absolutely. Anything with a battery in it. Name a few things in the room with batteries in it. Cell phones, laptops, computers, yes. Those are all basically DC devices, okay? Most of your electronic devices, if they got batteries, they're DC. Solar cells, you know, anything such as that, DC. And that's one reason that solar conversion is a little harder to do, because if you got a solar panel out there collecting light, producing electricity, it's DC electricity. If you want to get it on the grid, you have to convert that to alternating current, AC electricity. So you always have some loss of efficiency when you have to do that. Alternating currents, what's happening with those? Yes, that's what I was talking about. The movement, just back and forth, back and forth, back and forth. When you get down to it, the electrons are not moving far, and what they are moving, they're just staying in basically almost the same local position always. The charge motion is oscillatory, back and forth, back and forth. There is no net current flow. Whatever flows this way, in just a fraction of a second, it's flowing in the opposite direction. It's just back and forth and back and forth. Now, we still talk about it as current, movement of charge. It's just that it's moving back and forth rather than moving one direction. So that's alternating current. Advantages or disadvantages of AC over DC? DC over AC. What's that?
AC can go a much longer distance.
Which one? AC, you're absolutely right. DC, if you're having to move electrons in the same direction always, then you typically have a great deal of line loss, especially if you move very many. AC, and we'll talk about this a little bit later, you can alternate, you can adjust voltage and current, and as long as you're not moving much current, but at a high voltage, you can avoid a lot of line loss. You're absolutely right. Alternating current goes much further, okay? Just about everything in your home except for your computers, you know. In fact, anything that doesn't have some type of a big black box on it. Now, some of these may be in a plug. If you have the big black plugs, you know that's a converter, AC to DC, okay? AC coming in, DC going to the laptop. But anything else, just a standard plug like this, that's going to be AC. Just general rule, okay? Now, I can't believe that they have so little, so few examples here. There is an example given, which is an excellent, excellent example. They just don't have it on the slide, and they do all the work in the book. So let me read it to you, okay? In most cars, your battery's up front, right? Okay? And about how long is a car?
16, 17 feet.
Second? 15 to 17 feet, is that what I'm hearing? Yeah, that sounds reasonable. That would be a few meters, right? Okay. Especially if the battery wasn't all the way at the front and your thing. Is it? What kind? A what? A Dodge. I didn't know that.
A lot of the German cars, a lot of the, because of the space under the hood and weight,
Right.
they put the battery in that.
Wow. Okay. I knew the hybrids were that way, but I didn't know the. What's that?
A battery like this long.
Oh, really?
It's a long battery.
Oh, really? What voltage is it?
It's
12 volts.
This, when they
And
built
the
that
cold
car,
cranking amps is what gets them. Some of them are like 1,000 cold cranking amps.
when Dodge built that car, they owned Mercedes at the time, so they were using some
Right.
of what they did in their car.
Right, exactly. And now it's Fiat, isn't it? So I don't know what Fiat does. Okay. So let's say we got a battery in the front of the car and your brake light at the back. Okay? Now, do you know about what the drift velocity for an electron is? About 1/100th of a centimeter per second. Okay? Let's see if I've got a dime. I think I do. Yes, I do. Okay. That dime is about a millimeter thick, which is 1/10 of a centimeter. So slice that dime into 10 equal slices. Okay? Can you imagine that? How thin that's going to be? That's how far an average electron moves in a second. Okay? That's all, folks. It's extraordinarily slow.
That's blistering right there.
What's that?
That's blistering right there.
Yes, exactly. So if the distance, let's say between the brake pedal and the brake light, let's do that distance. That may be about 2 meters, which would be about 200 centimeters. And that electron is moving at 1/100th of a centimeter in a second. It's going to take more than 5 hours before by the time you hit the brake and the light comes on. Wouldn't be very effective, would it? If the light bulb wouldn't do it until that electron had made its way that 2 meters down the car. Not going to happen. Wouldn't work very well.
They don't need no lump
What's that?
They don't need no lump anyways.
They don't what?
They don't need to know what I'm doing anyway.
Right. Well, basically what you're doing, the field is almost immediate. You press on that, the field set up, and then the electron right next to the bulb, right outside the bulb, it moves that 1/100th of a centimeter. In fact, every one of them moves that, and that's what creates the light in the bulb. It's the field motion is fast, not the electron motion. More than 5 hours. Amazing. All right. Then there's also a little mistakes and misunderstanding. What is electricity? Pretty nebulous concept anyway, but we know how to use it. We know a lot about it, but really what's actually going on is still somewhat a mystery to most people. Okay. So next we move to electrical resistance. All right. Now, if you go back to this diagram, you see for an electron to move, it's running into a lot of interference, okay? Because it's being pulled by protons that are all over the place, so it's not a straight line motion. It's bumping into things like nuclei or other electrons and stuff and being bumped around. So basically, there's a lot of problems for that electron to move down the wire. That's called resistance, okay? The tendency of something to get in the way, the loss of electron current energy, that's created by resistance. Two sources. One of these is collisions with other electrons that are also trying to move down the same pathway, and they are opposite. They're like charges, so they repel each other. So if one's going here, it gets close to this one, it's going to get pushed back, okay? But then also collisions with other charges in the material. Maybe it's like to go toward a proton or go toward a nucleus, which is positively charged, and get stuck there and before the field pulls it on away from there. So basically you have two types of resistances. Collisions with other electrons, which are repulsive, collisions with other charges, which tend to be positive, would tend to stick it up and keep it from moving as fast as you want. Well, a good old German scientist named Georg Ohm. It looks like George, but it doesn't. They pronounce it Georg. Any of you see the Sound of Music? The captain in that was Georg. Okay, that's his name. Georg. This was Georg Ohm. He studied this tendency. He knew that if you increase the voltage in a circuit, you would increase the current. But it didn't go up exactly the same amount. It was a proportionality constant. He called that proportionality constant the resistance. Okay? Different materials had different resistances. Okay? That gave us Ohm's law. And y'all are familiar with that, right? Probably ad nauseum. Okay? And this is the classic one that you use the triangle or the circle for. V is equal to IR, so your V would be in the top and I and R at the bottom. V on top, I and R on the bottom. Okay? There's two different representations of Ohm's law. V is equal to IR, I is equal to V over R. What would be the third representation of Ohm's law? Say again? Okay, and what would that be? Exactly, voltage over current. So the last one, and I'll get my pen activated here. Yeah, the dark color. R, I thought I would. Okay, there we got it. R is equal to V over I. Perfect. Okay? So, that's what resistance is. Now, we already have a unit for volts. What's that? Volts, okay? The parameter is voltage, capital V. The unit is also, that's one of the few times, maybe the only time in physics to do that. What's the unit for current? Amp, okay? So the parameter is I, but the unit is capital A. And how about resistance? What would we call a resistance? Oh, named after good old Georg Ohm. And since that's a person, what symbol should we use? An O, a capital O, right? Oh, why? Why didn't we use, give me a number, any number. Just a number. 100. So let's say we had 100 ohms. You see why we wouldn't want to use a capital O for that? That sort of looks like I forgot to slash my other zero. Most people don't slash zeros anyway. So if I didn't slash, that would be, I'd slash anyway, 100 ohms. I can't tell the difference. Maybe that last was a little fatter or something. No, you don't want that. That looks like the number 1,000. No, you don't, because it looks too much like a zero. So, what in the world do we use? We can't use a capital O. So we went to the Greek alphabet. And in the Greek alphabet, there is a letter that's very close to ours. No, it isn't. It's Omicron. But guess what the symbol for Omicron is? A capital O. Okay, so we can't use Omicron. But the Greek alphabet has two letters that start with O. The one that corresponds to our O is Omicron, but looks just like our O. But the other one is actually the last letter in the Greek alphabet, Omega. Now, they don't have a Z. I don't know what corresponds to Omega, but Omega is the last letter. I don't know if you've ever heard the phrase Alpha and Omega from beginning to end, the first letter to the last letter. That's the last letter is Omega. It doesn't look like a capital O. It's, as Alfred said, it's your capital Omega. They use a capital Omega because it's named after somebody. Okay? That's not a little omega. Do you know what a little omega looks like?
I never knew that was capitalized.
That is capitalized. A little omega is like this. Yeah. This is your little omega. In fact, I bet you use that when you're dealing with frequencies and stuff. That little omega is angular frequency. Okay? So that's a little omega. They use a capital omega, which is that symbol. Okay? That's your capital omega. That won't be confused. So now if you talk about 100 ohms, you say 100 ohms. No confusion there. You know what you're talking about. So, resistance is that characteristic of a material that resists the movement of charge. That's why they call it resistance. Okay? Now, this is not anything to do with what we're talking about here, but it is related. You don't need to know this for the test or anything. But there is an inverse quantity that's not the resistance to charge, but the ease at which charge moves, and that's called conductance. Have you heard of that? Now, conductance is the reciprocal of resistance. And reciprocal, you know, means 1 over. Okay. What's that? Q is charge. Okay? So we have this quantity called conductance. They were trying to figure out what unit to give for conductance. And it wasn't just one person that came up with the idea, or maybe he didn't want something named after him. I don't know. But in other words, they didn't have one. So they finally decided, let's just say again. I don't think so. No, that's impedance, and I think. Okay. Now, so they wanted to come up with a unit for conductance. Huh? Which is? Impedance is Z, isn't it? Okay. So, oh, you said C. Is that what you said? G. I don't know. Maybe some people do, but the concept of conductance, okay, they needed a unit for it, and this just shows how weird physicists are. Just another example of how weird they can be. They decided to name it a mho. Okay? That is the unit for conductance, a mho. How did they come up with that? It wasn't one of the Three Stooges. That's not the same mho. Ohm spelled backwards. That's exactly what they did. They spelled ohm backwards. Since it's reciprocal, they spelled it backwards. That's the unit for conductance. Now, they needed a symbol for it. Now, they've already used M for meters and millimeters and micrometers, and you just got lots of M's. So what symbol were they going to use for a mho? It stands for conductance. Any ideas? Any whatsoever? Here's the symbol for a mho. and upside down omega. Since it's reciprocal, they just flipped it over. There's no symbol such as that except for conductors, and that's the symbol for a motor. Right. It's bizarre. It's weird. And you really don't use it that much anyway, but that is indeed how they did it. This is a little on the weird side. This is just totally weird. Okay.
What's your abbreviation for conductor?
What's that?
The abbreviation for conductor.
I don't even know. I don't know what that is.
Like voltage,
V and, yeah, I don't know what it would be for conductors. Second? Capital G, is that right? Okay, I didn't know that. Okay, good deal. I know now. Learn something every day, right? All right. That's beside the point. Here is Ohm's law written in 3 different forms. Okay? Now, this is for most materials. Materials we call ohmic materials because they obey Ohm's law. There are some materials that don't. For instance, in your automobile engines, I know that you probably have thermistors in there somewhere, don't you? Those don't obey Ohm's law well at all because the resistance varies with temperature, and Ohm's law it shouldn't. Okay, so that's not an ohmic resistor. Okay, we're not going to do much on that. So let's talk about more concepts with resistance. The factors that make up resistance are these. The type of material. Okay, iron has a lot more resistance than copper. Silver has less resistance than copper. Aluminum has more resistance than copper, but less than iron. So every material has its own specific resistance factor, and we call that the resistivity of that material. The other thing that contributes to resistance is the length of the object. And if you think about this, I bet you've all experienced this before. Have you ever been running lots of hose, my grandmother used to call it hose pipe, across the yard for a long, long distance, and finally if you do hose to hose to hose and hose, finally get to the end and you turn on the water back there at the house and hardly any water comes out here, okay? Why? Because you've got so much resistance to the flow. The energy of the water is being lost as it goes down. Same thing here. The length of the conductor increases the resistance, okay? Now the cross-sectional area does too. How do you think this does? Bigger is going to be more or less resistance. Less resistance, the smaller the more resistance. Just like a kink in the hose, right? If you have a kink in your hose and the opening is smaller, less water is going to come out. Same thing here. So cross-sectional area is inversely proportional to the resistance, okay? And then finally, temperature also contributes, okay? A little bit, okay? Now, the classic example for this to me is the incandescent light bulb. Do you know what the filament is in an incandescent light bulb? Second? Tungsten, yes, exactly. Now, I read just recently that Thomas Edison, who developed it, actually used something other than tungsten on his first light bulb. Later they found tungsten was better. Oh, he tried hundreds or thousands of things that didn't work, but he found some type of carbonized fiber of some nature that did work pretty well, but then later they came up with tungsten that worked better. Second? Yes, absolutely. So, but tungsten has a lot more higher resistivity than copper does, aluminum, and other things. So that's one reason we use it, the type of material. Now, how about that filament in the light bulb? Long, short, whatever. Okay, you would think it would be short, but if you ever look at it, it's a coil. And if you think about it, if you straighten that thing out, it probably becomes fairly long. So, yes, to increase the resistance. The material, tungsten, is more resistant than your good conductors. The length is longer than you would expect because they made the coil in there, and then they usually go around like this. How about the cross-sectional area? If I had one, It's about the thickness of a hair. Very, very small, so again, very large resistance. Now, don't know if you realize it, but temperature also comes into play. Have you ever had a light bulb blow on you? Sure, okay? Most of the time, when does that happen? When you first turn it on. And you know why that's true? Because, second?
Temperature changes so quick.
Okay, you're both on top of it right there. What is happening is that little wire at a cool temperature is going to carry more current than at a higher temperature. And since it's cool when you first turn it on, if it's a little on the weak side and you first turn it on, that's more current than the wire can handle, and that's why it breaks. Now they do go out sometimes as you're reading along, they've been on for an hour and suddenly goes, it just wore down. But most of the time it's right when you turn it on because you have that surge of current because the wire is cold. So temperature also is a factor. Now, and here's the picture that shows this. The type of material, what the resistivity of that material is, the length of that material. The longer it is, the more resistance. The shorter it is, the less resistance. Cross-sectional area, the bigger it is, the less resistance. The smaller it is, the greater resistance. Temperature, the higher the temperature, the more resistance, because those molecules, the electrons, everything else are moving faster, and there's more bounces, more collisions, and stronger collisions, so they don't move as fast. So higher temperature, greater resistance, lower temperature, less resistance. Except for one really strange material, okay? Well, and no, it's part of that. These things called superconductors. I'm just guessing right now, I think there's probably been at least 4, maybe 5 or so Nobel Prizes in physics for superconductors, because these are just amazing, amazing materials, okay? Quite often, they're not very good conductors at all at normal temperatures, but for some reason, when you drop them to very low temperatures, which of course would increase conductivity, it doesn't just increase it, it makes it phenomenally low. High conductivity, low resistance. Negligible resistance at very low temperatures. Now the earliest ones they found, when they said very low temperature, they meant very low temperature, like about 4 Kelvin or something like that. Really, really, really cold. Don't get much advantage out of them because it takes so much energy to get down to that temperature. You can't save anything from your lack of resistance. But over the years, and that's why several Nobel Prizes have been won, other scientists have developed more and more materials that are superconductors at higher and higher temperatures. They're still not very high, like maybe 20-something Kelvin rather than 4 Kelvin, or maybe 35 Kelvin. I don't know what the latest are, but very low resistance. Very negligible resistance at very low temperatures. And like I say, sometimes these are pretty lousy conductors at normal temperatures, but they become superconductors at very low temperatures. And they're quite often compounds, not things like tungsten or copper or silver or aluminum, which are metals. They are oxides of metals and things like this that you would think, why would that even conduct at very low temperatures as it does? So that could be a good paper topic. Hint, one of my largest classes, and so far I have one and only one paper turned in, right? You can only think of one. Yep, only one. Okay. So that's, please folks, you realize of course we got class this week, next week, and I think we have class one day of the following week, and then finals on the last Thursday. Okay? So you don't have much longer. You basically have 2 weekends left, that you can work on a paper. Please don't put it off. Okay. So, superconductors. There's many possible papers you could find on superconductors. I'm not pushing it, but that's just one possibility. All right, I think we're ready for example 6.3. So let me go back and see if I can find some space to work on it. There's some. 6.3. A light bulb in a 120 volt circuit. What's that a measure of? 120 volts. Voltage, of course. This is the one and few that uses the same parameter as it does unit. Now, when you say 120 volts, what do you almost know automatically? What kind of circuit is that? Second, AC. You better believe it. You don't run into 120 volts DC. If you do, someone's going to get shocked pretty badly. Something's going to burn up really quickly, okay? It just doesn't happen. You don't have that kind of voltages DC generally. Okay, so it's a 120 volt circuit switched on, the current of 0.5 amperes, 0.50 amperes. They said that was a current. What's the symbol for current? I, okay? Okay, the me generation here, okay. Flows through the filament. It's a light bulb. What is the resistance of the bulb? So what are we looking for? And what symbol for that? Second? That's the unit. What's the symbol? R. Capital R. And how is R related to V and I? Pretty exciting stuff, huh? Second? What's the formula? V over I, exactly. V over I. So that would be 120 volts divided by 0.50, what unit? Amps. There I did it. And what would that give you? 240 what? Ohms, exactly. Ohm. Okay. 240 ohms. Okay? Make sense? All right. I think we'll have room underneath this for the next one. What current, in this case, what are we looking for? What current? What's the symbol for current? I. So this is your unknown here. What current would flow through an electrical device in a circuit with a potential difference of 120 volts? So 120 volts is what? Voltage, okay, same unit for your parameter and your unit, right? One of the few ones. And a resistance of 30 ohms. So your resistance of 30 ohms. Okay? What would be your current? Yes, exactly. I would be V over R, which would be 120 volts over 30 ohms. And that would be, zeros go out, and that would be 4 what? Amps. Okay. And let's see, they didn't give us any significant units, so I imagine they just leave it 4 amps. Perfect. Good deal. Does that make sense? Ohm's law, one of the easiest, simplest, most direct things we can use. Okay. The thing is, we just didn't have enough letters or symbols that we could use. So, yeah. Just like for micrometers, we had already used little m for meters, little m for millimeters, the m for millimeters. What we're going to use for micrometer? Went to the Greek alphabet for a little m, which is a micro. Okay? Yeah, pretty common for them to do that. All right, so there's electric circuit. Okay. Resistance. Now we'll move on to electrical power and electrical work. Now, someone remind me, what is power? I've already used it as an example once today. What is power? It's what? Not yet. We're going to get there in a minute. What is power in general? Say again? It's the rate at which you're doing work or using energy. Joules per second. the time rate of change of energy. That's what power is. Okay? Work, of course, is joules. How much energy is being expended or spent on something. So, 3 circuit elements contribute to work. Okay? And we've seen these before, and here we have them again. I don't know why they say contribute to work. They just make a circuit. Your voltage source. What is voltage source supply? What is volts? In units? What is a volt? What are the units for volts? I know it's volt, but what is the fundamental, more fundamental than that? Joules per coulomb, energy per charge. That's what a volt is. How much energy each charge has, that's what a volt is. So, of course, voltage source, that would be energy per coulomb, joules per coulomb. That's really related to work, okay? And probably to power as well, because power is joules per second. So you can see in work it's just joules. So surely they contribute to work because it deals with joules, which is work or energy. Your electrical device, basically what are you interested in the electrical device? The load. And usually what characteristic of that are you concerned with in the last 2 examples we just dealt with? The resistance, exactly. Okay? And then you have the conducting wires, and that complete the circuit. They maintain that potential difference across the device because generally the conducting wires are good conductors, low resistance, so therefore they don't cut down, they maintain, that's why they use the word maintain, that potential difference across the device. Now always, there's got to be a little bit of loss, but it's negligible. The input wire is usually at the higher potential than the output wire. That's why we usually say conventional current goes from high to low. The output wire is sometimes called the ground in AC circuits, okay? And because they're going both ways, it's really not one at higher potential than lower. We just usually call the output wire the ground in AC. Now, there typically is no potential difference in the conducting wire, okay? That's why birds up on the electrical wires don't become fried birds, because there's no current that's going to go through them, okay? They have to be grounded in order to be electrocuted. Huh? Or touching another wire. Yeah, that would work too. The second house we lived in Birmingham, we rented a house for a year, and then we bought a house, and after a short time in that house, we got us a dog, a puppy. And she was a really smart little dog, and a really stubborn little dog. And we wanted her outside most of the time, or at least I did. I was working for Southern Research at the time, and I was going on a lot of field trips down to Florida or Tennessee or other places, meetings and stuff, so I'd be gone sometimes for a week at a time, come back, and I left one time and then came back and the dog was in the kitchen. Oh, well, she can come in the kitchen now, but she just can't go into the dining room, okay? And the next time I came home from a long trip, she was in the hallway. Well, yeah, but I don't let her in the bedroom, okay? And the next time she was beside my wife's side of the bed. I thought if I go many more trips, she's going to be my side of the bed. I got to stay home for a while here. But anyway, fortunately, this is weird. She got fleas, and then she started getting sent back to the kitchen. Or we got.
She got sent back to the kitchen because she got fleas?
Yeah, so she wouldn't be. Well, my wife didn't want her on the carpet right next to her side of the bed. So, but actually, she got put outside until we got the fleas taken care of. Yeah, and she did outside, and the rumor is she may have stayed in it once or twice, but I don't know. We have a kennel in our backyard now. The dog goes in there to play a little bit, but she sure doesn't want to be closed up in there. They sort of ruin the roost. But anyway, this dog, we found out, could get out anytime she wanted to, and we didn't know how. You go to work. She was a retriever, by the way, she was a golden lab mix. So she was a pretty good sized dog. I'd say about 70 to 80 pounds. No, in her backyard. Had her in the backyard, chain link fence all the way around, and she still was getting out all the time. Number one, we found out that she realized the latch on the gate, if she pushed it with her nose in a certain way, she could get it sometimes to flip up and then she'd be out. So we started wiring it shut. So she couldn't do that anymore. So then she started digging her way out under the fence. So I started first driving stakes down where she would get out and stapling them to the chain link. She somehow managed to get out. That dog, 80 pounds, could go through the smallest. She could flatten out worse than anything I've ever seen. What was that, Dundee or something like that? You know, go under anything. So after that, I started putting barbed wire between the posts, thinking that was going to stop her. It just scratched her back for her. You know, she didn't mind at all, okay? And finally, a neighbor said, the only way you're going to keep that dog in is to put electric fence, okay? Electric fences. No, not in college. Well, we didn't have an invisible fence, no. They have that nowadays. Back then, it was electric fence. You actually ran a little wire, DC circuit around there. And the neighbor said, don't worry. All it's going to take, she's going to get zapped one time, get her nose on it. She'll never get close to it again.
Right through it.
Huh?
They'll run right through it every time.
What's that?
Our dogs would.
Yeah.
Those electric
Right.
fences, we had a bunch of them.
Yeah. They said she won't, she'll get shocked once. She won't get close to it. You can turn it off. Just leave it up there. They'll think it's on. This dog. She would go up real close to it. We thought she was listening to it, and that may have been, she could just maybe hear the vibration, or she got her whisker close enough so she could tell if it was on or not. Something she would do. She would do that and find out whether it's on or not. But her favorite thing to do was for me to be working in the yard, and she'd come up next to me and rub and push me into it. If I jumped, she knew it was on. So, I mean, she was that evil of a dog. I mean, she was a smart dog. Well, anyway, we had this run around the bottom, and it did keep her in pretty well. And one day, I came home, and there was a squirrel. You know, it jumped up and hit and touched. It was grounded, and it was frozen. It was electrocuted there. I didn't mind it too much. I don't care much for squirrels, but anyway. The bird is not going to get it because the bird's not grounded. The squirrel got it. Okay, zapped.
Unless they stand on it, just right.
What's that?
If they stand on it, just right, they'll get it.
I can't hear.
If they go over towards the transformer and stand
Oh,
on
yeah.
the transformer, they'll get it.
Okay, and that happened near our backyard too. The alley behind the house, a squirrel shorted out the transformer, and we were out of power for a while. But it was a fried squirrel. You know, I mean, it was bad news there for a bit. We think that may be what happened that made our dog scared of loud noises then, because after one of those power outages, she would not tolerate thunder or firecrackers or anything else. Before that, never bothered her. We think that transformer blew right near the house, and it must have sent out enough current, charge through the air that she did not like loud noises for the rest of her life. What's that?
You said you put barbed wire.
I put
You put it around the bottom.
around the bottom, tried to keep her in. Didn't work. You just use some scratches back.
So take the chain link fence and the barbs stick out on top. They
Turn it
have
over.
the fence installed. They have
Yeah.
installed the other one.
Yeah. I don't think anything would have worked with Casey. She was too stubborn of a dog. And
Probably would have built a ladder.
what's that?
That dog probably would have eventually built a ladder.
she made out. She was clever. I mean, we could not, if she thought we were leaving and she didn't want us to go, she was going to find a way out. But she was also a retriever. So when we come home from work, we knew that she had been out because she went around and retrieved trash from everybody's yard and brought it to ours. And so my wife would drive and say, she's out again, and we'd have to, in fact, it wasn't just trash. It would be kids' toys and people's shoes and things. So we'd have to go around the neighborhood. We got to meet lots of neighbors. Excuse me, is this yours? Is this yours? Our dog brought it into our yard. And in fact, Later we found out how much she got around.
He said it's supposed to be one of the smartest dogs.
She was a pretty smart dog. When we went to vote one time, it was just down the road at the school, so we both walked down there with the dog, and my wife went in to vote, and while I stayed out with the dog, and then I went in, and my wife, when I was in voting, when I came back, my wife said, there were just so many kids that came up and said, oh, there's Casey's mom, you know. We didn't know who the kids were, but they knew our dog's name, you know, and she was well known in the neighborhood. But that's beside the point. Okay. Good old Casey. All right. So, what is power in circuits? Now, I think you were getting ready to give it to me. Power in circuits is this what you were going to give me? Power is current times voltage. That's one formula. Okay? Now let's think about that formula. What is the unit? What are the units for current? Amperes. And what is an amp? What is current? We talked about it earlier in the class. The time rate of change of what's moving with the current? The electrons, which are your charge. Charge per time. Time rate of change of charge. So charge is measured in what? Huh? What's the unit for charge? Q. Q is a symbol for it. What's the unit for it? No. Okay, Coulomb. Coulomb per second. That's what current is. And what do we say voltage was? That one you just said. Joules per Coulomb. Energy per unit charge. Joules per Coulomb. Guess what happens? The Coulombs cancel out. And what do you have? Joules per second, which is power. Exactly. Joules per second, power. Okay? That's why P is equal to IV. What's that? Yeah, and the unit for power is in watt, capital W. Second? Yeah, Joules was James Prescott Joule. They named energy after him. They named power after watts. James Watt.
Well, they were dead when the names got put on.
Sometimes, yeah. Most of the time, I would say. They did it to honor him. James Watt was a Scottish engineer and physicist who did a lot of the work with power, though he used horsepower. In fact, he's the one who defined what a horsepower was, 550 foot-pounds per second. He's the one that did that. But when they came out with the SI unit, they named the SI unit after him.
A lot of them scientists use dead scientists' names to say something was not right. They can say, well, that ain't my name.
Yeah, it's his fault, not mine. Okay, so that's what a watt is a joule per second. Okay, now, I assume most of you are probably use the same power company. What's that? Okay, so every month you get they like a power bill. Is it really a power bill? Why not? It's an energy bill, exactly. We talked about this before. Your electric bills, you're not paying for power. You're paying for energy. Now, as you just said, one definition for power is IV. The other one is power is energy or work over time. Okay? And it actually be either energy or work. They're the same units, remember? So, how could you get energy out of that equation? Yes, multiply both sides of the equation by time. Time goes out here, and you get energy is equal to power times time. And this power would be in kilowatts, and time would be in hours. So your energy would be in kilowatt hours. So you're paying for kilowatt hours, not kilowatts. If you look at your bill, it doesn't say how many kilowatts you use. That really doesn't make sense. It's how many kilowatt hours you use. And that's the energy used. Okay? Which is quite a bit of energy, by the way, too. So let me clear this so you'll be able to read what they say next. And that will be your energy bill. Now, they do all sorts of weird things. I wouldn't do this yet. I would say energy times time, that gives you your power times time, that gives you energy. Energy is power times time. Then the rate at which you're doing that, dollars per kilowatt hour.
That's what changed different.
What's that?
Every time they feel like changing.
Yeah, exactly. They changed it. I can remember back when they bragged about being 3 cents per kilowatt hour. Now it's nowhere close to that. They don't brag on it
Now
anymore.
they won't even tell you
Yeah.
how and why they changed.
No, it used to have to go through the Public Service Commission once a year, but now they seem like they change it anytime they want to, because they own the politics. I shouldn't say that. Now, multiply that by the rate, and that gives you dollars per kilowatt. But this is in watts, so you have to convert the watts to kilowatts. It's 1,000 watts per kilowatt, and that will then give you your cost. Weird formula. I never do it that way. There's much easier ways to do it. Okay, but you pay for energy, watt hours or kilowatt hours. Okay, so most of the time we're not going to use that complicated of a formula. It's far easier to do it another way.
You just sell power back to the
Yes.
company in this state. I know some states don't allow it.
I don't know if Alabama does or not. I would hope they do, but I don't know for sure. Will the power company buy your energy if you're producing it? Like if you have a wind turbine or if you have solar cells? Yeah. I think in Georgia they're required to, because my younger brother works for a power company, and boy, did they dissuade their customers from doing it. But I think they're required to. I just don't know about Alabama.
They do their own stuff, solar, wind turbines, and they do it all. I don't think they hook up the power no more.
Now, say
We
that
don't
again.
have Alabama power where I live.
Oh, you have TVA?
Yeah, TVA.
Yeah.
North Alabama.
Right.
Even though their dam is on our way, we
Right.
don't get Alabama power.
Is that right?
And we get charged for it.
Yeah. which lake are you on? Huh?
Watts Lake.
Watts?
Watts.
Watts. Okay, I'm not familiar with that. We have a place in Smith Lake up in Winston County.
You got any fish up there that's worth anything?
What's that?
Is the fish up there good?
Yeah, they say they are. I haven't had them up too
Oh,
much.
you don't fish?
But
That's pretty deep.
it's a really deep lake, and they have some
Really clear.
really clear lake too. And they say they have some real big ones in there, but they're hard to get. But you know,
They cost about 20, 30 foot.
yeah. Smith Lake goes down like this. It's not a broad lake like what's the one over near Gadsden?
Pickwick.
Second.
You talking about Pickwick
Or center.
on the Tennessee waterway?
Watts
Uh,
Lake's over close to.
No, I can't think. Yeah, I can't go. My mind's going blank on the name of that one. But anyway, Smith Lake, you can always see real close to the other side, but it's really deep in between this. It's a finger lake, lots of fingers all around it. Okay, so there's your power. Now, couple of examples before we move from here. Okay, I think we'll do them here. Okay, example 6.5. A 1100 watt hair dryer. What's that a measure of? That's a power measurement. Watts, power. Okay? Is designed to operate on a 120 volt circuit. What's that a measure of? Voltage, of course. Okay? How much current does the dryer require? So what are we looking for? Current, and that's I. Very good. And what's the relationship between power, voltage, and current? Okay, current would be P over V, because P is equal to IV, so I would be P over V. So what would that be? 1100 watts divided by 120 volts. I think I'll need a calculator for that one. 9.2 what? Amps. Very good. And by the way, that's a pretty hefty amount of amps. Okay? But anything that uses lots of current, high amps, that's going to cost you lots of power. Okay? Lots of energy is being expended there. So anything that produces heat, hair dryers, clothes dryers, actually your AC system, even though it's cooling, is pulling a lot of heat out. Ovens, okay? Not microwave ovens, they cook differently, but anything that produces a lot of heat, you better believe there goes your meter really fast.
Microwave, you got the 800, 1200, 1500 watt microwave.
Oh, really?
They throw a lot.
Yeah, if you got the real big ones like that. I think ours is so old it's not that big.
When microwaves first started coming about, people just started adding to their kitchen, but the house wasn't wired for one device pulling that much power.
Okay.
So you have to run a dedicated circuit.
Okay, I didn't realize that. I knew that, clothes dryers and ovens, of course, they're 240, they're not even 120. And most of your air conditioners, if you had window units, most of them would be 240s. And certainly the big unit downstairs is going to be at least 240. But I didn't know I guess
still
like
110, they just
drew a lot of current. Yeah, right. Because they were lower voltage, right? Okay, that was example 6.5. Let's go to 6.6. An electric fan is designed to draw 0.5 amps. So 0.5 amps is a measure of what? Current. What symbol? I. That means yes in Navy. Okay. In a 120 volt circuit, of course, that's going to be your voltage. What is the power rating of the fan? How are we going to get that? What's the power rating of the fan? Okay, P is equal to IV, okay, which would be 0.5 amps times 120 volts, and that would be what? Is what? 60 watts. 60 watt. So that fan's about like your average light bulb, 60 watts. The only reason light bulbs are pretty high is they produce a fair amount of heat. Whereas your compact fluorescents and your LED bulbs, they'll say 60 watt equivalent, but then when you look at the actual wattage on them,
you're talking about the output of the light.
yes, exactly. That's what they mean, equivalent to a 60 watt incandescent, but when you look at it, they're what? 13 watts, something way lower. So you know you're saving a lot of energy with those. All right, and here, sure enough, we have a 100 watt bulb at the top of page 152 on the right-hand column. We have a finishing sander, and it's so hard for me in my old eyes to read this. It's what? Yeah, that's at the bottom, isn't it? What's that? That's a it's 120 volt. That's something that you feed sticks and stuff into, and it shreds it in the mulch. Okay, I was trying to see the rating on it. It's 120 volts, 8 amps. They don't give you the wattage, do they? But it'd be pretty easy to calculate, right? 8 times 120? Yeah, 960 watts, almost a kilowatt. Okay? And the finishing sander, I'm having trouble reading that. Volts, 120. 1.6 amps? Okay, so then you could figure out what its voltage rating was too. Power rating was too. All right, then, okay, let's move on. We already did those. Before we get to magnetism, people behind the science, good old Benjamin Franklin. Did you think of him as a scientist? Most of the time we think of him as maybe a politician, a statesman, or something like that. He was a pretty good scientist and a pretty good engineer as well. He created, invented what they call the Franklin stove, which is a potbelly stove that a lot of places use for heating for centuries, okay? He did the work with electricity we know about. A really bright character, okay? By the way, there's also and by the way, if you want to write on Benjamin Franklin, this blurb can give you ideas, but this can't be your source. Remember, you got to get an outside source. Anything in the book is not a legitimate source. You have to find something outside. This can give you plenty of ideas. Yes?
I know you got criteria on the paper. You got the citations and all in
Yeah, whatever your format you choose to do, follow that format. Yeah. You only need a couple. I mean, 1 or 2 or 3.
MLA, APA.
Your choice. I'll handle any of them. Okay.
Yeah,
I'm not trying to make it something you have to reinvent the wheel for. You go with what you're familiar with. But Benjamin Franklin at one time, I think I've said this before, I believe was also a ambassador to France. I'm not absolutely certain, but I can almost guarantee you if they were still around, and I think they were, he probably interacted with Coulomb and Ampere and some of those others, or whoever there were around that were doing things with them. I bet you he was right in the middle of all of that. Okay, they have summary of electrical units and the quantities. Charge is Q, which is number of electrons times the fundamental charge of an electron. Okay, electric potential. Voltage is joules per coulomb, which is energy or work per charge. Electric current is coulombs per second, or charge per time. Electrical resistance is volt per amp, and electric power is current times volts, which when you multiply current, which is coulombs per second, times voltage, which is joules per coulomb, the coulombs cancel out, you get joules per second, which is of course what a watt is. Okay, they also have shocking costs here, and it's fairly interesting if you take a look at some of those. I've already mentioned several of them. Anything that produces a lot of heat is going to cost you a fair amount of money as far as electricity. The things that are lower in heat, it's not going to be generally as much. But coffee makers, toasters are going to be a bit on the higher side, whereas can openers, they don't produce a lot of heat. Okay. Anyway, let's look at example 6.7. Here's one of those cost problems. So let me get rid of the ink and go back and let's fill it in here. The power. Okay, what is the cost of operating a 100-watt light bulb? What's 100 watt a measure of? That's your power. Very good. For 1 hour. What's that a measure of? That's your time. Okay? If the utility rate is 10 cents per kilowatt hour. Yeah, when's the last time we had some of that? Okay, so the rate was 0.10 cents per kilowatt hour. Okay. How would you figure out the cost? What's that? It's 10 cents per kilowatt hour. 10. 10 cents per kilowatt hour. Okay? Let the units be your friends, folks. Here you have watts, here you have hours. You multiply those together, what do you get? No, watt hours. Okay? So that would be 100 watt hours, right? So let's do that first. The energy or work, I'm going to put energy, is equal to 100 watt hours. The only reason I didn't use work is the unit for energy is watt, is for power is watt, and I didn't want two W's in there, okay? But let's convert that to kilowatt hours. What would that be? How will you convert that to a bigger unit, giving you a smaller number? Divide it by 1,000, that would give you 0.1 kilowatt hour, okay? And then your rate is 10 cents per kilowatt hour, so multiply this by that, and you get 0.01.
Yeah, but how much can that power up?
I'm sorry?
How much can that power up?
How much can it power up? I don't know what you mean.
Like 10 cents for 1 kilowatt an hour. 1 kilowatt per hour, whatever you said.
Okay, it's 10 cents. That's the rate that they're charging you per kilowatt hour. Okay,
How
there.
much do you use in the average day?
Oh, you use a whole lot more than that.
That's what I'm saying.
Yeah,
How
right.
much does it
Right, okay.
Power up.
Yeah, this one light bulb, a 100-watt light bulb for 1 hour, only costs you a penny. But of course, if you run it for 8 hours, that's 8 cents. But that's one of the cheapest things there. You also have 2 or 3 of these 100-watt bulbs on most of the day. So yeah, it can add up really, really quickly. Yeah, I know what you mean now. Okay? So that was 1 cent. What's that? Right. Exactly. And the thing is, my younger brother works for an electric power company, so he's not trying to convince anyone to be very conservative. He just retired, by the way, but anyway. He always liked to leave his lights on just to show, it doesn't cost that much, because light is pretty cheap. It's the air conditioner, the heater, the clothes dryer, that's going to run up the bill, okay? But what's that?
I believe in running the AC from the home.
Right.
Nobody's up in the house, you did not turn it on. I'm like, huh. So furnace when I get in here.
Yeah, it's burning up.
1,500 watt floodlights running outside.
Yeah.
On all 4 corners of the house.
Yeah, you can add up. You really can. All right, that was example 6.7. Let's look at example 6.8. An electric fan draws 0.5 amps. We've had that one before, haven't we? 0.5 amps. What's that a measure of? Current. What symbol is that? I. So there's your current. In a 120 volt circuit. What's that a measure of? That's your voltage or potential difference. Very good. What is the cost of operating the fan if the rate is 10 cents per kilowatt hour, same as before? So your rate is 0.10 cents per kilowatt hour. Okay? So what is the cost of operating the fan? Okay? Well, you got to get to watts at some point. What do those others? Do they give you anything close to a watt?
60 divided by 1,000 first, just to get to kilowatt hour.
Okay, no. To get your power, which is in watts, right? What's that formula? Yeah, current times volts. So that would be 0.5 amps times 120 volts, and that gives you 60 watts, okay? But you need that in kilowatts, so what would that be? And which would be 0.06 kilowatt, okay? So that would be, if you multiply this by that, then you get 0.006 or 0.6 of a cent per hour, because your kilowatts cancel out, and that's per hour. So that electric fan is going every 2 hours will cost you a penny, 1.2 pennies. Okay, that's pretty inexpensive, and that's why they say running your ceiling fans or something like that. Now, a ceiling fan is probably a little bit more than this, but you can sure do a lot of cooling. Yes, ma'am. Yeah, I'm sorry, I can't hear you. My hearing's bad.
I'm selling tickets for Taste of Bessemer. It's on Thursday
Okay.
at the Bessemer Civic Center. It has over 50 vendors. Do tickets are $15.
$15.
$15.
Okay. Are you trying to sell it to the class? Or?
Anyone that's interested in going.
Okay. When will you be available?
Today.
Okay.
Or they can go to the Bessemer Chamber of Commerce and get the tickets.
Is that price buy any food?
Sir,
Is that price
the
buy any-
tickets gets you all the free samples of the vendors, and most of the vendors will give plentiful samples. Because last year there was vendors giving a whole entire meal.
Okay. This is Thursday. Noon.
From 4 to 7.
Oh, 4 to 7 in the evening.
Yeah.
Okay.
And I have tickets with me if anyone's interested.
If you let us out at 3:30.
Wait a minute. Wait a minute. Slapping me streaming. Okay, never mind.
Yeah,
Okay.
come on, that was work. We don't want to get there and eat table scraps.
You said 4 to 7?
Yes, sir.
We get through at 5:45. You got plenty of time.
Messed
Yeah.
over everybody.
This-
man.
No. They
Just
bring
next door.
food if we.
Come on now, what?
No. Well, why don't you do this? If you. What, this is math class?
No, this is physical science.
Physical science? Make it some kind of extra credit if they get.
Wait a minute. See what worse than y'all are. Okay. No. We're right in the middle of class now, so could we get? How long are you going to be around?
Field trip.
I can. Do y'all ever take a break in your class?
No.
No.
Seldom. No. All the time.
You just
No.
gave us a break back. You
Okay.
It don't count.
We usually don't count
breaks.
Okay.
He's still recording.
No. It's right at 3 o'clock. We usually take one about 3:30.
Okay, I can come back about 3:30
Okay.
if anyone's actually interested.
Are any of you interested in purchasing? I don't have that with me today.
only if
I
I can
can't.
get my full $15 worth. And I believe
I hear the violin music in the background, don't you?
If he'll
So-
let us out at 3:30, I'll go.
We'll let you out at 3:30.
Okay. It doesn't sound like I just don't have.
I was actually looking for you originally.
Yeah. Okay.
you might get hungry that day.
Of course I will, but I'm always hungry. But yeah,
All right,
sorry about
yeah.
that. Yeah. I can't believe they walk into a class in session and do that. But it is for a good cause. Okay, so the answer is 6 cents per hour is all that fan is costing you. So when they're talking about using your ceiling fans or just any old fan, you can sure save yourself a lot. Running that AC, you got a big blower in that that's going to be costing a lot, plus then all the cooling of it.
I got an attic fan that I can
Yeah. Oh, and those are pretty good too, as long as the temperature is a little cool on the outside. All right, so that finishes the part on electricity. So now we're ready to start the part on magnetism. Okay? Okay. All right. So, electricity, the first half of the chapter, approximately. This is the second half. Actually, it's the shorter half. Now, remind me, we've got to stop at 3:15, so we're only got about 15 more minutes, right? Is that right? No. Yeah. Because we're we're doing the lab today. 2 hours of class, 1:15 to 3:15. 2 hours of lab, 3:15 to 5:15, and then 30 minutes of test at the end, 5:15 to 5:45. Okay. The lab probably won't take you that long. So let's at least introduce the magnetism part here.
If we skip our breaks on Thursday, how early?
The lab on Thursday isn't going to take you very long either. So I have a feeling you'll be able to get away in plenty of time.
What do we do that last today?
We don't have time to do 2 labs today, I don't think. Okay.
We take a test.
What's that?
We take a test today.
Today is chapter 4 test. Yeah. It's the last 30 minutes today. So when you finish it, you can leave. So let's look at magnetism. Electricity and magnetism, are they related at all?
Magnetism and what?
Electricity.
Yeah.
Big time. But for a long time, no one had a clue they were at all. Magnetism, actually, people have known a lot more about magnetism for a lot longer than they have electricity, and they've had uses for magnetism, whereas for a long time all they used electricity for was to shock people, in parlor games, that kind of stuff. But magnetism's been around a while. The earliest ideas, they knew that certain rocks, basically, contain naturally occurring magnetic materials. There's the common name for it was lodestone. It's basically an iron ore that was naturally magnetic. Okay? The mineral name is magnetite of that rock that they call lodestone. Magnetite. Now, magnetite and hematite, identical chemically. You can't tell any difference apart, except typically hematite is not magnetic, whereas magnetite is magnetic. So why is there a difference? Chemically, they were exactly the same, but some are magnetic, some are not. Now, magnetism is characterized by poles. In this way, it's similar to electricity because electricity is characterized by charges. Two different charges, positive charge, negative charge. Magnetism is characterized by poles, and we typically call them north poles and south poles. Now, really, the better name would be a north-seeking pole or a south-seeking pole. Would be a preferable naming, but everybody just calls them north and south. Now, there are other materials rather than lodestone or magnetite, which is an iron ore, but the only three elements that do show up as naturally occurring magnetic materials are iron, which is lodestone, cobalt, which is pretty rare, it's not that common, and nickel. Okay? Nickel is not that common, not nearly as common as iron, but these are called your ferromagnetic materials. Ferro basically means iron. The symbol for iron, does anyone know what it is? Fe for ferro, okay, ferrous. Okay? Ferromagnetic materials, iron, nickel, and cobalt. Now, most of you, I don't see a book handy, but if you've got a book and you've got the periodic table, and it may not be in the back of the book like this one is, but it's in chapter 8, somewhere in chapter 8, you'll find, if you find iron in the Fe, right next to that is cobalt, and right next to that is nickel. Those are the three only naturally occurring magnetic materials, period. Iron, nickel, and cobalt. Iron, cobalt, and nickel. Okay. The modern view. They've known this for years. Now we know they're associated with magnetic fields. Just like electricity is associated with electric fields, magnetism is associated with magnetic fields. Now remember what was the rule for field lines in electric charges? Where did the field lines go? Field lines. No, from positive to negative. Always emanating from the positive toward the negative. So the field line always points positive and negative. What's the rule for magnetism? Always going from north to south. Exactly. Associated with this, the field lines go from north to south poles. Because what you do with an electric field, you imagine a small positive charge. You put that in the presence of the magnetic field, the direction of the small positive charge would be away from a positive charge toward a negative charge. That's the field line. Well, you do the same thing with a magnetic field. You imagine a little magnet there, a little compass needle. Put it in the presence of a magnetic field, the north's going to put it away from the north toward the south, always. So the field lines go from north to south. Poles. Okay. Now, whereas there's some similarities, and by the way, the rules for charges, what's the rule for attraction and repulsion of charges? Like charges repel each other, unlike charges attract each other. How about for poles in a magnet? Same thing. Like poles repel each other, unlike poles attract each other. So there seems to be some characteristics. Here's the big difference. You can have an isolated positive charge. You can have an isolated negative charge. You cannot have an isolated north pole or a south pole. If you have a magnet, you got them both. The magnetic field and the poles are inseparable, and the poles always come in north-south pairs. Well, what if you had a bar magnet? North pole, south pole. Okay? And here is Terry. Okay? North pole, south pole. Bar magnet here. What if I cut off the north pole end? Okay, yeah. Now you have a north pole, south pole, and a north pole, south pole. You now have two magnets. You always do. You can't avoid the north-south pair. What we say is magnets are always dipolar. Not bipolar, that's a mental thing, but dipoles. Always dipoles. The field lines go from the north to the south. Can't avoid it. Light magnetic poles do repel still, unlike poles attract. Very similar to what you have with charges. Okay? So, this is the example I was just given. If you have a bar magnet, break it in two, you now have two bar magnets, the north and the south. And by the way, if this is your bar magnet to begin with, if you were to drop iron filings on that, where would they all go? Yeah, they just get big hairy thing. Nothing would stick in the middle. Absolutely nothing. Or hardly anything. Okay? You break it in two, and guess what? Here, here, and here, here, okay? Where you had no magnetic attraction of iron filings here, now you get a whole lump of them here and a whole lump of them there. So no, you can't avoid that. Break it again and again and again, and every time you just get more magnets with just as strong a pole here as here. Okay? So you just get more and more magnets. All right, does that make sense? Here are the field lines, and here's how you distinguish those. You imagine placing a little magnetic compass in the direction that the compass points, the north points, that's the direction of the field line. If you put the compass up here, it'd be pointing here, here it'd be pointing there. So that shows where the field lines. Always from north to south. Yes, it is, because the field lines are pointing that way. But, yeah, that's true. I was doing... Okay, yeah, if you weren't in the presence of a stronger magnetic field. I was taking soil samples. It had something to do with a lawsuit. I never knew which side of the lawsuit I was collecting for, but I was doing it. It's in between. I'd worked in Southern Research for 8 years, and then they had a change of government, and they did away with external funding by EPA, and that's where most of our funds were coming from. So our whole group was let go. We were doing radon research. So for that year, I was doing adjunct teaching at Jeff State. I was doing any job I could, tutoring, whatever I could, until I found the job here. So for about a year, I didn't have. And one job that came up was doing some soil sampling, again, for a lawsuit. I didn't know which side we were on. I was just doing the sampling. And what I had to do, I'd go out, it was over in Anniston, where they had the PCB contamination that was causing a lot of people to have cancers or be exposed to things. So I was doing soil sampling there. I was mapping out, taking samples all around this area where they had the contamination to see how broad the contamination was. And I was using a compass to guide my way through the woods. I mean, it was really thick woods, up and down hills, and stepping off my distances. It was pretty approximate, but I was trying to do the best I could. So I was following my compass, trying to lay out the places where I decided I needed the samples. And I got to a place, and my compass just started doing weird things, and I could not figure out what has happened to the compass. So I went back, and it was doing fine. So I came back again, and then I stepped through an opening, and there were all these big power lines, going back and forth, and they were just sending out wacko signals so my compass wasn't following the Earth's magnetic field. It was getting disrupted. So yeah, this is being disrupted by that. If you're in the presence of stronger magnetic fields, yeah, then it doesn't point north anymore, or it points wherever the field lines are. It's just in the presence of the Earth's magnetic field, the field lines point north. Okay. If you were standing on the North Pole, I don't know where it would point. It would try to point straight down. That would be hard for you. Yeah, exactly. You have that issue too. We'll get to that a little bit later. Okay. What's that? It depends on where you are, but where we are, it's less than 5 degrees. It's only a small deviation because we're pretty close to the line between the magnetic North Pole and the real North Pole. We're awfully close to it. Over in Seattle, I think you can be 20 degrees off, and in Maine, you could be probably 15. So we just happen to be in a place where it's only a couple degrees deviation. Okay, we'll get to that a little bit later. Okay. I think maybe we better stop there. Sources of magnetic fields. Okay? And almost the next thing is going to be exactly what we were just talking about. All right. So we will pause there. And if you want to take a quick break, you can. Let me, just to save a little bit of time. What's that? Oh, you're wanting to get to eat. I can tell you're governed by the stomach, huh? Yeah. Okay. Let me pass out. I may just pass out these. You'll keep one and pass at least 2, maybe 2 more. I'll let it start. Keep one and pass 2. Okay. All right. Yes, sir. Oh, good deal. Thank you. Okay. So why don't y'all take a you can take a fairly generous 5-minute break. And I guess since the room's open, we'll probably just use the one down where we've been going to 259. It's a little cramped in there, but at least we don't have to move stuff so far, so we'll go with that. Okay. I'm going to put this on. You got that right. Okay.
Probably why he didn't remind.
Okay. All right. We're doing electric circuits. Everybody got a copy of the lab? No. Oh. Got here, didn't you? Boy, you talk about squeezing in under the wire. Okay, James, shut up. Let's see what we got now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Everybody's here too. Okay. What'd you say? I couldn't hear. Oh, you score much better on your test if you are here and paying attention the whole time. Yeah, absolutely. Big rewards. Okay. All right. Electric circuits. Everybody got a copy of the lab? Yeah. And you've read this. Hopefully, you were reading while I was setting up. You'll see a lot of these terms, the words, the phrasing, just like we did in class. A little bit on nomenclature. I think all of you are familiar with this. Anytime we're representing a battery, and that's what our power supplies are representing, batteries. They're not exactly, but they are representing. Notice what the convention is. A battery is a series of long vertical lines and short vertical lines, alternating long and short lines. The long lines represent the positive pole, the short lines the negative pole. And these batteries like this, that would be the one that you see on front there, upper left, that would be a 3-cell battery. Notice is one long, short, long, short, long, short. The positive on the long end, negative on the short end, and we'll be doing this a little bit later. We will talk about batteries in sequence, in series, and batteries in parallel. It seems like we should have already done that in the book, but we didn't. It's confusing to me. We should have already hit that. Let me just look and see. We didn't miss that somehow, did we? No, that's coming up. For some reason, that's at the end of the chapter. Strange but true. Okay, so we will be doing some like that in today's lab, even though we haven't had it in class, but I think you're all pretty familiar with it. Hopefully you are. Okay, so that's your battery symbol. Alternating long, short lines, and the positive being the long and the negative the short. And that would be a 3-cell battery in series. Okay? We're not doing AC, so we're really not using a ground, but most of you are familiar with that. Now, go down underneath the battery and you'll notice the resistor there. Resistor is a jagged line that indicates the resistance. They put a circle around it, they're indicating the resistor is actually a bulb. So that's what we'll be using today, is a bulb. Now, if we had a variable resistor, we'd put an arrow on it, meaning we could change the resistance of it. We're not doing that. An open switch is there. We're not going to deal with switches today, even though some of the figures will have them. We're not going to deal with them. Now, if you had a circuit and you had a wire crossing another lab but not joining, you put a little loop over it, indicating they're not really touching. I mean, they're not really, they may be touching, but they're not connected. But if it's actually a junction, then you put a dot there, indicating they are joined there. We're not doing that today either. So don't sweat that. Now, what you're to do, the very first thing in the lab, is, if you turn the next page, page 180, you'll see here a figure of a bulb. Okay? Now, that bulb is not complete, is it? You got your filaments up there, but not connected to anything. How is it that bulb's going to work? Say again? Okay, the little dotted line up top, that's the filament. Okay? It is continuous, it's just very small, that's why it's a little dotted. Okay? But the bottom part, there's nothing connected. How are you going to make that bulb work? Now, this is, by the way, it doesn't really matter AC or DC, but we're going to assume a DC. What is going to be the case here? Okay, very good. The very middle of the bottom there is actually a conductor. The little area above that and the black on either side, that's an insulator. And then the outside of the bulb, of the connector there, that's actually metal again. Okay? So for this to work, you cannot have those two wires touching or crossing each other. Okay? You have to have one to the outside and one to the tip. Otherwise, it's not going to work. Now, when you get over to your stations, there's 3 stations set up here. I wish with this bigger class we had more, but I don't. You'll see here some old bulbs here, and they're pretty corroded, so that's why they're old bulbs. But you'll notice here's the tip, there's the insulator, the black is the insulator, and then this is metal. You have to be connected, one wire, and you can't see inside here, but one of the filaments is to the exterior and one's to the tip. And every station has one of those. Actually, one of them has a little bit better than the others. I think it's that one. You can actually see in there a little bit better and imagine that. And that's the one sitting, I think, off to the right there. Okay? But, so you fill in 2 connectors there to show how that bulb is going to work. I just sort of described it to you. You have to put it in on the bulb. Okay? Draw something in there. Now, if you have any doubts, ask me. I don't want you to get it wrong, but I'm going to let you be the judge whether you understand what it's asking for. The picture of the bulb, figure 20.2, that you just put in 2 connecting lines to make that bulb work.
Draw it straight to that bulb.
Say again?
This bulb on our sheet.
Okay, no, this bulb right here.
Yeah, you draw 2 lines.
No, you don't have to draw from there. You have to connect these somewhere so that bulb, when you plugged it in, would work. Just on the figure 20.2. Just on the bulb. Don't do the box yet. We're going to get to the box in a minute.
You mean draw this to here?
This is what you're talking about, right? Drawing the wire.
Absolutely. Right. I think I do.
Hey, is this what you're talking about?
And it is a pretty good idea.
You want me to do?
Yeah. Go out, draw all the way down to that bottom. See, it looks like it's cutting off there. Go down to the very bottom. But other than that, good idea on this one to have pencils. You can use ink if you want to, but if you make a mistake, it's going to be a mess. But no, this doesn't show it any better. I thought it might. But you can see where the wires on the outside go to, so the ones on the inside must go to the same thing. Okay.
Well, when you get home, you turn your lamp on, take the bullet out, and stick your finger in there, and you'll find both of those.
Let's not say we did, okay?
But if you wet your finger and stick it in there, you really find.
Or your tongue. That might work, yeah.
It's like a
That's just cruel, that.
All right. So everybody got 20.2 done.
Yes, sir.
Any doubt? If you do, ask. Okay? So that's the first part.
You got
Now, the second part in the box, in the rectangular box here, basically what I want you to do is draw circuit 1. Okay? And you can leave off the switch. Draw circuit 1 in the box up here. Circuit 1. Just, you can leave off the switch, so you don't even have to put a switch in. Okay? Notice you have a battery there. How many cells does it look like that is? 1 cell. Which is the plus and which is the minus? Long as the plus, the short is the minus. Okay? Now, if you draw that circuit number 1, here's what you're to do. If you flip back 1 page, it says, on page 180, that's that page you're looking at, make a sketch of your circuit. Use the symbols given in the introduction to show exactly how you construct the circuit to make the bulb light. Draw an arrow. This is all you have to do. Draw an arrow to show the flow of conventional circuit current and a second arrow to show the flow of electron current. Once you draw that figure, number 1, leaving out the switch if you want to, you don't need the switch in there, and then all you do in addition to this is draw 1 arrow showing conventional circuit current and 1 showing electron current.
I use my own little symbol like that battery right there.
Okay, I guess that'll be fine.
I already drew it now.
That's fine. That's perfectly okay. Okay.
Did you jump ahead, Mason?
Okay.
Where'd you put it, man? I just drew it, but I saved wire. You saved wire? I saved wire. Why run it all the way? You ain't even got a battery. There's my battery right here. He's got power.
Yeah, look at the symbol. There's your battery symbol.
Yeah, well, I want you to look at his battery. This is my power right here. It
Okay.
comes and runs to my bug. Well, my bug, I just got a little kickoff for the ground.
Okay.
That's how I got it.
Uh-huh.
You said 1 wire. I just saved you a little bit of wire.
Okay. Well, that would be very appropriate for a AC circuit with a
Let me
DC.
go and extend this
Yeah,
out.
go and do it on the round. We're doing DC.
Conventional is for the.
What's that?
You said conventional negative positive, right? What's the positive and negative?
Okay. You got your book?
That's how they use
Conventional is positive, negative. High potential, low potential.
That's how they use
Electron is the other way. Huh?
That's how they end the grounds and stuff. That's how they end the wiring diagrams for cars, which is DC current.
Yeah.
Drop down, ground.
Right.
And
it's
it's like,
got the-
none of,
You
lots
say
of the cardinals are
conventional
all like
positive,
that.
negative,
Actually,
and
really nothing does.
Right.
It's grounded by somewhere, usually on the ground.
Yeah, I know, but if you'll notice, your battery still has two poles, right?
Yeah.
And the one pole is to the frame, isn't it? So, yeah, it's still got it. Yeah. Yeah.
Conventional is positive, negative, and the other one is negative.
You got it.
What's the other
Electron.
one called?
Electron. If you turn back one page, there it is. Conventional current, electron current. Okay, everybody got the second part done.
Yeah, so more or less, like, I mean, not really in context, but like on a battery on the car, we got like the thing backwards. Like if the electrons are actually coming out of the power side. And you confuse me. Like the flow of electrons is what electricity
Right.
is. So if there's power coming out of the battery, flow of electrons, why do we have a positive symbol on what would really be electrons going out?
Right. The electrons are negatively charged, so they leave the minus and go to the
Why we
plus.
got a positive?
Because that's the direction they're going to.
You getting deeper into this topic than we need to get.
Yeah. Somebody's wanting to go home. Okay. All right. So you got 1 and 2 done. All right. Now the rest of the time, now what do we got? Added up 4, 9, 10, 11, 12, 13. Is that right? 1, 2, 3,
You said
4, 5,
TV,
6,
don't
You did say it.
do it. You
Yeah.
said TV.
Okay, we got 3
You said I know
stations, so
electricity.
that's going to be 4 people per station. Sorry about that, it's pretty crowded. But one station's going to have 5. So 2 teams will have 4 each. 1 team will have 5 on there. What's that? Yeah, and I've actually done the first circuit for you. Okay? So 4 people to each station, and 1 station will have 5.
What you saying? Yes.
Looks like we got 4 over there, 3 over there. We need either 4 or 5 there, and okay. Somebody didn't really hear that. So that's 1, 2, 3, 4, 5. So the other 2 will have 4 each, 4 and 4. Got it. Okay. Now, folks, don't do anything until I tell you. Okay? Because guess what? These bulbs will blow out if you over.
I took this off the board. Where does it go?
Huh?
I took this off the board. Where does it go?
Okay. Let me get
I took this off the board. Where does it go?
Now, all right. Now, what I want you to do all of you see the on-off button? You might have to move your board a little bit. It's the red button upper right on the power supply.
Yeah.
Okay, you see it, okay? Now, you can turn it on if you want to. And then there's a switch, okay? A round knob over on the left, okay? Slowly increase that until your bulb is not too brightly lit, but just nicely lit. Increase that until it's just, don't get it too bright. Cut it down, down. You're going to burn my bulbs up. Down. Okay, that's pretty good. You can go a little dimmer down there. Little dimmer. Little dimmer. Little dimmer. Little dimmer. Okay, that's looking pretty good. How about yours? Let me see.
This bulb gives you a 10.
Okay, is that nicely lit? Okay, good. All right, read your voltage. Oh, y'all are way too high. Wait a minute.
What? You said good. Look how
Yeah, I
bright
know,
it is.
but where y'all set it? Okay.
I think we let
Oh,
the
okay.
out.
All right.
Turn it up now.
No, you're fine. You can even turn it down a little if you want to.
What you do if smoke come out?
What's that? Okay. Then you turn it off. Okay. So read your voltage. Now, folks, that's going to be, take a good look at your bulb, not the others. That's your standard brightness. Right there is your standard brightness. Okay? You've got your,
That's our standard.
and record your voltage there. Okay? Now,
The voltage here, 5.5.
that is circuit 1. That's your standard brightness. Okay, now all of you will find another bulb near your table there, and you need to set up circuit number 2. Now, what's similar with circuit number 2 to circuit number 1? Anything?
This is our boat
Now,
right here.
in our,
Yeah, that's your voltage. Say again?
where do we put that voltage at?
Okay, write it on results number 1. Brightness of the bulb is your standard for the normal, and don't answer any more, but you can write down the, well, wait, actually. Go back to the back page, the very back page, circuit number 1, simple circuit, and you can put down observation, standard brightness. Second observation, put down your voltage. Okay? Those are your 2 observations for number 1. Okay. Now, go back to page 180 and look at circuit number 2. I want you to tell me what's similar between 1 and 2. Anything?
There's 2 loads.
Second?
There's 2 loads.
Okay, that's a difference. What's similar? Yes, the battery is the same battery. So you're not going to change your voltage, but you are going to put an extra bulb in. And why is this bulb related to the first bulb? In series. Now, what does that mean? Same current goes through both. So let me see how you're going to do that. Remove the black wire. You see the other bulb? Okay.
We changed the battery in the car.
Okay. Don't break anything. You need help from you. No, the bulb, one of those is broken, but it still works. Okay. I want to point something out to you.
trying to figure out why
Wait just a second. Notice the lines. You pull this out of here, that's where the current is. So this is going in here. Got it. All right. Okay. Might need to do those one. Yeah, let's do those. Okay. Now.
Slim.
Okay, yeah. Press down on it. Yeah, okay, got it. Y'all got yours? Good?
Yep.
Once you got yours. All right, fantastic. Now, on every one of these, on your observations, here's the 2 things to observe. Brightness of the bulb. It can be brighter, dimmer, or standard. You saw what your standard was. What is it when you put 2 bulbs in series? With the same voltage. Okay? The second observation you make is what happens when you remove one of the bulbs? What goes away? The light goes off. Exactly.
It's like
Okay.
the same thing as cutting the wire.
Say again?
It's the same thing as cutting the wire. You ain't got no-
Exactly. Okay? But you need to observe that and do it.
What if the house number 2, that'll go to the back page also.
Okay, now this is the back page. The back page, yeah, you don't do results until you finish the back page. So the very back page, your observations are, is it brighter, dimmer, or the same? And what happens when you remove one bulb? That's going to be standard on every one of these. Okay.
So we need to write what happens when you remove one bulb?
Yes. Okay?
Where's that question at?
Okay? Under observations, the last page, page 183. Yeah, there's no question. There's a question.
We removed the bulb.
And what happens?
Let's give the circuit.
Okay. All right. So what you do is here, you put dimmer, and then what happens? Everybody got it? 2 observations. Brighter, dimmer, or same standard brightness. Number 2, what happens when you remove one of the bulbs? Okay? Now, tell me what, look at circuit number 3 now. Now, here's what I do not want you to do.
Kick it up.
I don't want you to double your voltage. I do not want you to do that, because you're going to blow some bulbs. But what I want you to do is go back to, that's back like number 1, except you're going to increase your voltage. That's all I want you to do is increase it a little bit from what your standard was. Increase it a little bit, and when you know it's a difference, stop, and then you answer the question. What are your observations? Brighter, dimmer, or the same? And of course, there's no 2 bulbs to do. So what did you find? When you increase the voltage just a little, what happens? It gets brighter. That's all you do. Shut it down then. Don't keep increasing. Okay? I don't want you to blow the bulb. Okay, but wait. You're not doing number 3. Number 3 is go back to 1 bulb, so you don't increase the voltage. Okay, of course, do it. Okay? Yeah, I know. Okay? Has everybody done it? Number 3. Okay, once you've done it, shut it down. I don't want to burn the bulb out. Okay? No, don't crank it how much? Just a little bit. Okay?
It don't matter. We know what goes to.
Okay? Just crank it up a little. Okay, good. Okay, good. That's enough. Okay? What happened? It got brighter. There's no 2 bulbs to it.
You still want to think about when you take a bulb out?
No, okay. There's no 2 bulbs. It's only if there's 2 bulbs. What happens to you if you remove a bulb? Okay? Now set up number 4. Tell me similarities or differences to the others. Similar to number 2, except increase the voltage. Now this time you can double your original voltage. On number 3, I didn't want you doubling it. This time you can. Okay?
So you said do what now?
Okay? You got the bulb? Okay? Now double the voltage approximately.
I can't see it.
Okay, that's good enough. Okay. Okay. Now, what you got? Okay. You answer the 2 questions. Number 1, brighter, dimmer, or same, or standard brightness. And number 2 is what happens when you remove a bulb. And you answer this on the table. This is circuit number 4. Okay? When you double the voltage, did you do it? Okay? You answer the question. Brighter, dimmer, or standard brightness. That's one question. The other, what happens when you remove the bulb? Okay? And what was your answer to the first one? Standard. Very good. Excellent. Okay? Everybody got observation number 4?
Yes, sir.
Okay. Now number 5. What do you see similar or different?
Parallel.
Okay, the 2 bulbs are parallel, and what do you have otherwise? Yeah, you go back to your standard voltage. Back to your standard voltage. Now, do you know how to do 2 in parallel? If you don't, ask me, and I'll help.
2 batteries.
That's what these wires here are for.
2 batteries. 2 batteries.
Okay. If you need help, ask. I'll be glad to give my opinion.
I wouldn't trust you to spell that word.
What you got?
But that is real for you.
Okay, yeah,
You couldn't even plug in the TV. I don't know what's worse than not
What I was
knowing
saying
how to
is,
plug in. I can't do.
Yeah.
behind 1,000 cc.
Very true. You can find one for $60 grand. I did it for them. So I found some Outlanders that before they
You go back to your standard voltage, not the high voltage.
adding a shorter range one.
Hey, y'all think that's brighter than it was in series?
No, that's standard.
No, that's standard.
Okay. So your two questions you answer are the brightness, is it dimmer, brighter, or standard? And the second, what happens if you remove a bulb?
One stays.
Say again?
One stays. Disconnect the bulb. One bulb stays.
Okay. You go back to your standard voltage, don't go high. Go to standard voltage, whatever you started with. Yeah, sometimes these things drift like crazy. Old Dart is just really nervous there. And that's one reason it's a good idea to turn them off in between, so you get the heating inside.
I think your leg.
It's like getting something sideways.
Okay. Y'all got number 5 answered yet?
Yes, sir.
What you get?
We got standard and one still below.
Okay, sounds good. Everybody get that?
Yes, sir.
Okay. Now what's the difference between 5 and 6?
Yeah,
Okay, did y'all get yours? Orange juice. What happens if you remove the bulb? One stays lit. Okay, very good. Did y'all get number 5?
Yes, sir.
Okay, I know y'all did.
Pretty positive.
What did y'all get for 5?
Best group you got.
Get anything? That's about right. Whoa!
Smoked it.
All right. This goes to the high side. Come on, do it, Ron. Be quiet. Yeah. Go back to your standard voltage.
Brighter. 8.4 volts.
Standard voltage, whatever you
Got
started
it. It's a juice. What kind of juice is going to it?
with. Okay?
Yeah.
Okay, now, again, on number 6, don't double the voltage, just increase the voltage. Don't double it, just increase it. What you get. Don't leave it on too long either. Okay?
Don't run the fire bill up.
I don't want anything blowing up. I don't want to have to buy new bulbs. Okay? You don't have to double, just increase. And you answer the same 2 questions. What are they? Brightness and what happens if you're removing the bulb? Right? What you get? Brighter and the other stays lit. Very good. Okay? Everybody get number 5 then. You already done 6? Okay. Let's talk about 7 and not actually do 7. Turn off your machine for now. Cut down the voltage, whatever. Okay? Let's take a look at number 7 and you tell me what's going on.
It's gonna be bright. I don't know.
Okay? You say 7's going to be brighter. Anyone else?
One bulb and parallel wire. I don't understand what that means. Like
Okay.
they're both gonna get the same. What's it?
What you reckon is going to happen then?
They're both gonna get the same power.
Say again?
It's gonna be standard.
Okay, you think? So I hear a standard, I heard a brighter.
It's still getting 5.5 volts.
Okay?
On ours,
Any other ideas?
What do you mean when you say one bulb in parallel with wire?
Okay,
Like,
with the
can
wire.
you show me what you're talking about?
Okay? Now we're not going to do it because I don't want any burnt rubber here. Okay? This out. And we'll go That's very good.
Well, that ain't gonna work. You about to blow this? You about to
Exactly.
burn
That's
the
why I
wire.
didn't want you to turn anything off.
Okay, well that's why I didn't understand what you're talking about. It's kind of vague. One bulb in
Okay, well,
parallel with
here's a
wire.
picture right here.
Oh,
You've
what
been
is
supposed to
it?
be looking at the picture at a time. Number 7.
Long goal.
Okay. Are y'all still doing?
Burn up.
Okay. You got the answer yet?
Well, you really need to draw that. We just say the wire.
Double the voltage, just increase the
I'm gonna
voltage.
sell it smoke out.
Okay. What can you tell about the brightness? Tell about the brightness?
It's standard.
Okay. Are you standard voltage or you increase voltage?
All time.
Switches and series.
Roll time? That's what the lady said. That's what I said.
Don't say nothing.
That's what he's saying. Go, say, go
Hey,
Braves.
look, man, don't get kicked out right either.
Okay. And what happens if you remove the bulb?
Well, isn't charger just so?
Okay.
Yeah.
Now increase the voltage just a little. Don't
I had
touch
someone
it.
down a little bit after that.
They look at the body.
Yeah, they get brighter. Okay, stop.
It's like,
More.
guys, we got a
Okay.
problem.
And what happens
Keep
if
it to
you
yourself.
remove
So
the bulb?
this is a brave sound. Shut up, Slim. Who cares?
This is the very first time.
I was
she's
gonna
ever
say,
waited
exactly.
to sit down.
Okay. So you've done 5 and 6. Now don't do 7. Let's think about 7. Look at the picture of 7 and tell me what's happening.
My question is, do you want me to draw all that out, or can I just say it's gonna burn?
Okay. Why?
Good.
So you
You can't have a circuit without a load.
Okay.
You got a circuit without a load, then you got to
I'll take you a raise.
Okay. That is I say that electricity is a lot like students. It follows the path of least resistance.
Oh yeah.
Okay?
That's true.
So all the current is going to go through the wire. It's not going to go through that resistance in the bulb. So almost nothing goes through the bulb. It all goes through the wire, and like you said, it would burn up the wire. That's why I didn't want you to do it. Huh? It's called a short circuit. How is that different from an open circuit?
Open circuit, have current.
Okay, how can you tell the difference between the bulb? The bulb won't turn on either one of them. So you can't tell a difference just by looking at the bulb whether it's open or shorted. You'd rather it be open than shorted. If it's shorted, you're going to have problems. Something's going to catch fire. Open circuit, you can fix that.
So you don't want us to put nothing to 7?
Okay, number 7, what it says to put there is, I didn't want you to actually do it because I didn't want you burning up any insulation. One bulb parallel with the wire, show with arrows how the current takes the path of least. Well, number 1, you answer the question. Is the bulb brighter, dimmer, or standard? Nothing. So the bulb doesn't come on. That's the first one. And then the second one, you can either use the figure that's on number 7 on page 180, or you could draw it in the box on 183, whichever you prefer, and show where, as it says here, shows how, with arrows, how the current takes the path of least resistance. So where does the current go? Through the wire, not through the bulb. So that's why the bulb doesn't come on. So you can either draw the circuit there or use the picture that's already on page 180 and draw it there. Either one. Just draw it somewhere. All right. One of the questions, the first one was, what happens to the bulb? And I think someone said, doesn't even come on. So that you can either say dimmer or it doesn't come on, either one. And you know why, right? Okay. Now, number 8, and remember I said we're not messing with switches. What is number 8 then exactly equivalent to? Okay, and what? No, okay, the battery's in series, the bulb, the load's in parallel, which is just like which?
It would depend on the switches.
What's that?
It depends on if the switches were put on.
Okay, yeah, and we're not messing with the switches.
Well,
That's
if the
what-
voltages was the same, you would have, it would be like turning the voltage down.
Okay, no, which of these other circuits here is just like number 8 if you just ignore number 6? It's just like 6. And what was the answer to 6? brighter, and one stays on. Okay? Because otherwise it's identical. The battery's the same, and you got two bulbs in parallel. Now, we haven't talked about parallel and series yet in the book. That's why I find these labs, they don't really do well, but y'all know what you're talking about. So, yeah, of course. Okay. Now you can answer the question. If you filled out the table correctly with your observations, brighter, dimmer, or standard, and what happens if the light goes out if you remove the bulb? I mean, what happens to the other light if you remove one of the bulbs? If you've answered all those observations, now you should be able to answer the results 1 through 7. Okay. Now, let me also point something out to you. Number 1, you've already answered it probably. I think you wrote it there, right? Okay. Number 2, which circuits had bulbs that were dimmer than normal? Look at your observation table and find the ones that are dimmer and put those circuits down. So that's going to be one thing. You're going to put some numbers of circuits down. Which ones were dimmer than normal? But then the second part is explain why. If you just put the circuits that were dimmer, you get credit for that. But if you don't have an explanation, you don't get credit for that. Number 3, which circuits had bulbs that were brighter than normal? Look at your observation table. If you put your observations correctly, you should be able to write down those circuits, but then you also need to explain. So there's 2 parts for number 2. There's 1 part for number 1, which is describe which circuits have bulbs with normal brightness or standard brightness. So you answer that for number 1. There's no explanation. Number 2 and number 3 both have explains on them. Number 4, which circuits did removing one bulb cause the other to go out? Again, answer which circuits that happened from your observations, and then explain why. Number 5, same thing. In which circuits did removing one bulb not affect the other one? You answer that with a number of circuits, and then you do an explanation. Again, if you leave off the explanation, you don't get credit for it. And then number 6 is one answer. Well, I mean, it may have several parts, but describe the general requirements, so it's going to be more than one, for any circuit to function. We talked about it in class. We talked about it today. Okay, and then number 7, you answer that however you want to. If it's blank, you don't get credit for it. If you answer it reasonably, you get credit no matter what you put down. Any questions? Is that making sense? If you have questions, please ask. And by the way, I should have already called roll again. So I'll mark it now. James is still here. Terrence is still here. Yeah, there you are. Okay. Camp is still here. Yep. Slim is still here. Dart is still here. Mason's still here. Samuel's still here. Ryan's still here. Alfred's still here. Jeremy's still here. Charles is still here. Oh, by the way, Brittany came in today, but she hasn't made it to class yet. I saw her before class, but I haven't seen her since class. Trevor's still here, and Terry is still here. So everybody but Brittany. All the Y chromosomes made it, the X chromosome didn't. Okay. Okay, we have, second? Oh, good. Okay. If you have any questions, please ask. Don't guess. So if there's no questions, I'm going to pause this so we just don't have a lot of dead time and you don't hear James up here snoring.